Today I'd like to introduce you to a concept that is of great utility to us in our classical mechanics, and that is the notion of a system's center of mass. Now, as a mathematical idea, the center of mass is not particularly complicated, because all it is the weighted average of position. Now, as you see me write it here, you might get a little bit disoriented at first, but I'd like you to consider that you take a course in physics or whatever subject, and you're told by your instructor that your grade is a weighted average. Well, the whole weight of an entire course is probably 100% if we're doing things in a typical fashion. And so what I'll be told is that out of that 100%, some fraction of those percentage points are the tests and the quizzes and the homeworks and whatnot, much like the syllabus for this course. And so if I want to calculate the grade, what I have to do is add up every score that I get, multiplying it by its weight. Tests probably more important than homework assignments and so on. And then I calculate the average out that way, a weighted average. In the same way, what I'm going to do is look at a classical system. And by system, I mean the same thing that I've meant by the term system all along. And that is that I have some group of objects, in principle interacting one with the other, around which I choose to draw an imaginary boundary. Everything inside the boundary is part of the system. Everything outside the boundary is external to the system. And so in this system, there are a bunch of objects that have different locations in space. They're their positions. But they also have different masses. If I were to calculate simply the average position, then I would add up all the vector positions in space and divide, and then I would discover that average position. But instead, what I'm going to do here is define the center of mass position. Now, I'm doing it in one dimension, simply because defining the center of mass in 3 dimensions is as easy as any other vector quantity. I could write the x center of mass position and make an identical definition, which is the y center of mass position, the z center of mass position, and so on. So there's nothing, no new information in doing problems in multi-dimensions. So I'll stick with the one-dimensional case here and say that I define the center of mass. By definition, the center of mass position is equal to, here in the numerator, the mass of each object, here m1 x1 plus m2 x2. So the mass is multiplied by their positions, m1 times x1 plus m2 times x2 plus m3 times x3 plus so on and so on and so on, for how many particles happen to be in the system. If I'm being really ambitious, I could imagine a system of a great many particles, whereas so far I've only talked about 2 objects colliding. But my system could have many objects. And so that's my numerator, and in the denominator I need the total weight of my weighted average, which is here the total mass, m1 plus m2 plus m3, and so on. That is the weighted average, the mass-weighted average of position that is known as the center of mass location for a system of particles. Well, it's a little sloppy writing it like this way, so what I'll do is I'll take advantage of some mathematics notation, and I'll write it as a discrete sum. Here the center of mass position is equal to 1 over the total mass. I see that my denominator here is going to be m1 plus m2 plus m3 until I'm done adding up all of the mass. So in principle, the denominator is the total mass, which I'll just call m, times the sum. The index I equals 1 to n, where n is the number of particles in the system, mi xi. So if you write this sum out, you'll see in the case if n is equal to 3, for example, I get the numerator of this previous step here, mix or m1 x1 plus m2 x2 plus m3 x3. And so this is my definition of the center of mass. It's written in a more complex, more compact way using the summation notation. Imagine that I am looking at a simpler system of particles where there are simply 2 particles being considered. Then I would simplify this by simply setting n equal to 2 and running the sum for 2 steps. And so the center of mass position for 2 particles, m1 and m2, is m1 x1 plus m2 x2 divided by m1 plus m2. So here I'm going to examine what the consequence of this, or what sort of properties this has, by imagining that I draw my x-axis here. So I'll choose a location along my number line that I call 0 and extend out here to the right the x-axis. And I'll put in this one-dimensional space 2 objects, m1 and m2, and I'll draw them here with different sizes, sort of implying that they have different masses. Well, that's not necessarily true. I may in a moment put some conditions on those masses, m1 and m2. And naturally, in this coordinate system, which I've arbitrarily chosen, there's nothing special about the coordinate system. In this coordinate system, they naturally have positions x1 and x2. Well, where will I find the location of the center of mass? The center of mass location for two objects will always be located somewhere between the two objects. Now, in order to find out exactly where, particularly when the masses are not equal, I will have to perform this calculation to find out. However, generally, and I think we all have this expectation, is that if M1 and M2 have different masses and M2 is the more massive object, which I've sort of implied by drawing the size of M2 larger. If M2 is the more massive object, then the center of mass position will be closer to M2. The reason why is that M2 with the larger mass gets greater weight in the average position, and that shifts the center of mass position towards M2. And indeed, it's true that based on this algebra, it's a necessity that the position of the center of mass be between them. Now, from time to time, you may have looked up above my head here as I'm lecturing on different subjects and seen these two objects that I have, two masses attached to a rod, much like the description that I put on the board here, where I have the large black sphere on one end, which in principle is more massive, than the small wooden sphere on the other end. And you may have looked at it while distracted from the lecture, hopefully not for too long, and noticed that the string that supports this apparatus from the ceiling is much closer to the large black mass than it is to the smaller wooden mass on the other end. This is because that is what many people, I think, would refer to as the balance point between the two objects. It's the location where the influence of the small weight on one side and the large weight on the other side equal each other out, and so the thing doesn't turn. That string is located at the center of mass position of that particular system of particles, and of course is closer to the larger mass. As an example here, I'm curious what would happen, though, if I were to choose M1 and M2 such that they're equal to one another. Because what I want to do is verify a suspicion that I have, is that if two objects have equal mass, then the weighted average of their positions should certainly be in the center. So I suppose this is in some way a test of this rule that I've written. And so what I'm going to do for my example is I'm going to change the location of 0 in my coordinate system. I get to choose that. It's quite arbitrary. And so in retrospect, maybe I look at it and I say, it would have been rather clever to put the origin of the coordinate system to be at the location of M1. That is, the position of M1 would be equal to 0. It doesn't hurt anything, and it probably simplifies my algebra. So I'm going to set x1 equal to 0. Then that means that x2 becomes a specific value, because if I decide that the distance between M1 and M2 is a distance d, then the distance from x1 to x2, that is the distance from 0 to x2, is equal to d. So that means that the position of 2 is equal to the value of d, and I'm going to assert, under those conditions, that m1 is equal to m2. Well, look at my algebra, what happens here. If the center of mass position is m1 x1 plus m2 x2 divided by the total mass, m1 plus m2, then when x1 is set equal to 0, this term here on the right vanishes. X2 becomes equal to d, m2 is just m, and in the denominator it's m1 plus m2, which is clearly 2m. The m in the numerator cancels the m in the denominator, and what I'm left with is that the center of mass position for a system of two equally massive particles is exactly what I expected. Its location is at the position that in this coordinate system is called d over 2. I want to point out a subtlety here, that when my answer comes out of a center of mass calculation, that answer is is coordinate system dependent. I got d over 2 as my answer, particularly because I chose the origin of my coordinate system to be where mass 1 is located. This is just reinforcing upon you, please, to appreciate the fact that coordinate systems are critically important, and where you may be solving problems on your own and carelessly really not think deeply about the coordinate system you're using, it's important to appreciate that your answers come out in the context of that. So I've defined the center of mass as a mathematical concern here, and you would probably imagine that I would not do so unless there was some utility to it. It turns out that the utility of the center of mass is fantastic indeed, extremely important, extremely useful. So what shall I do with this center of mass now that I have it? Well, what I'm going to do is reconsider my dynamics of particles, that is Newton's second law on the motion of particles, position, velocity, acceleration, in the context of the center of mass. So I'm considering here the dynamics of the system. The dynamics of the system not the dynamics of an individual object. I've spent time with Newton's laws drawing a free body diagram for an individual object and understanding its motion in that way, but now I'm considering the entire system, which can consist of many particles. So here again, I write my definition of the center of mass position, again in one dimension, because I don't have any need in particular to extend it to 3 dimensions. It's trivial. So if this is the center of mass position, defined as I've already said, then I can define the center of mass velocity. Quite easy, because I know that any position, whether it's x1 or x2 or the center of mass position or any position I choose in space, the velocity is defined as the derivative of the position with respect to time. So I would imagine that the velocity of the center of mass is the derivative of the center of mass position with respect to time. So let me go ahead and compute that. It's quite easy. In my center of mass definition, 1 over m is a constant. And the mass of each individual object in the system, mi, is a constant. The thing that's not constant with time is the positions of every object in the system. They are functions of time. And so I can take a derivative. Well, naturally, the derivative of xi with respect to time is vi. And so I can say here that the center of mass velocity is 1 over the total mass, the sum, I equals 1 to n being the number of particles, the mass of the ith particle times the velocity of the ith particle in product. Well, that's a familiar thing. When I see mass times velocity, I realize that this is the quantity of motion. This is the momentum. And so I could write this sum even more compactly, making pretty notation. 1 over m, the sum, I equals 1 to n being the number of particles in the system. Pi, sigma pi, is the sum total of the momentum of the system. Every particle in the system, or every object that I identify in my system, has some definite mass and definite velocity, and therefore a definite momentum. The vector sum, now I've been leaving the harpoons off here, but let's appreciate the fact that I know that momentum is a vector. The vector sum of all of those momenta is what I have been talking about in recent lectures as the total momentum of the system. So let me just write that total momentum divided by m. And so I write this here, p divided by m. And you say, well, it's not surprising because the p divided by m is the velocity. But here in particular, let's see what we have. What I've particularly discovered here is that the total momentum of the system, which I have said is a useful quantity, particularly in the context of the law of conservation of momentum, is equal to the total mass of the system multiplied by the velocity of the center of mass. That is, if the velocity of the center of mass were a quantity that was known, I need not go around and know the velocities of all of the other objects in the system, because I would find that it is equivalent to the mass times the center of mass velocity. A thing that's implying to me here, and I want you to let this sort of blossom in your mind, is that it's possible for me to treat a system of particles according to its center of mass position and its total mass, ignoring the individual particles. If I can pull that off, that of course would be a fantastic simplification. I'm curious, I can keep going with this. We know it's a very a common practice that we've done early in our physics. If I know the velocity of the center of mass, I could compute the acceleration of the center of mass simply by taking another derivative, and the same thing will happen again. Here's my velocity defined, 1 over the mass times the sum of I equals 1 to n being the number of particles, mivi. When I take the derivative of that, it's the vi that I'm taking the derivative of, and that vi will naturally be ai. And so the acceleration of the center of mass is 1 over the mass times the sum of I equals 1 to n being the number of particles, miai. Wait a second, miai, ma, I know what that is. For the ith particle, its mass multiplied by its acceleration is the net force that acts on that particle, the ith particle. It's the net force that acts on the ith particle. So I'll write in a more compact way that the acceleration of the center of mass is equal to 1 over the mass times the sum of I equals 1 to the number of particles of the force on the ith particle. I'm just going to add up all those forces. But every particle in the system, including the ith particle, the forces that act upon it can be divided into 2 classes. Those forces which are action-reaction forces, interaction forces with other members of the system, and forces exerted upon the ith particle that are external to the system. So there are, for any particle, I, there are external forces and internal forces acting. Well, I know, as a consequence of Newton's third law, and a consequence that I've been taking advantage of over the past few lectures, that the sum total of all the internal forces of the system is going to be equal to 0. So when I perform this sum, I equals 1 to n being the number of the particles of Fi, All that will be left over is the net external force, because all of the internal force will cancel. So I write it here. 1 over m times the sum of the external forces. Notice I dropped my index I because I'm not talking about the individual particles anymore. I'm talking about the system as a whole. And you can imagine when a force is exerted on a system, imagine my system is a system of balloons floating in the air, and the external force is the wind. How the wind exerts on each individual balloon in the group could be quite complicated. I'm not interested in that. I'm interested in the net external force on the system. And look what happens when I rearrange this to write it in an extraordinarily familiar form, that the net external force acting on the system, the complicated group of particles that I have chosen to describe as my system, the net external force acting on the system is equal to the mass times the acceleration of the center of mass. Again implying, just like my momentum rule that I wrote above it there, again implying that I can treat a system of particles as a single particle whose mass is the total mass m, and whose location is the center of mass position, and whose velocity is the center of mass velocity, and whose acceleration is the center of mass acceleration. There is a dramatic and extraordinarily useful consequence. Consider here this hammer that I have, rubber mallet, and think of it not as a single mass, but as a collection of masses. It was a little bit difficult to do, but of course it's composed of atoms, but don't go that far. Just imagine there are the little chunk of mass here at the end of the handle, and there's a little chunk of mass here at the end of the mallet on this side, and there's a chunk of mass here, and in your mind sort of divide it up into a system of masses. All of those masses have different positions in space. I could, in fact, make them different masses. And I can understand, even if I can't immediately compute, the center of mass position of this mallet. Now what I've done is I've drawn a dot on the mallet where I believe, sort of rough approximation, the center of mass position to reside. The mallet end is very, very heavy, so I'm not surprised to see the center of mass position, at least in an x-axis sort of a regard, to be close to the head of the mallet. That doesn't surprise me at all. In fact, if I sort of put my finger there, I'll find that that is a balance point, roughly, for the mallet, just like my mobile that's hanging there from the ceiling. So when this hammer moves under the influence of gravity, that motion is quite complicated. Here you see I flip it end over end, and if I watch it, it goes around in a crazy sort of circular motion with the head moving slower, then the handle moves faster, and it takes a little bit of coordination for me to do this, flipping it end over end. And the motion of any given part of it is quite complicated. For example, if I were to keep careful watch of the very end of the handle, I would find that it, well, apparently I was not keeping careful watch. If I keep careful watch of the end of the handle, it rises and falls, but at the same time, it's whipping around in circular motion. Drawing that trajectory in space is very complicated. In order to understand that trajectory, I would have to analyze the forces that act on that particular little chunk of mass at the end of the handle and integrate those equations in order to get the trajectory of the thing. But it seems to be a lot to go through just for the sake of throwing a hammer around. And so what I want you to consider is these two laws that we've just discovered. That the hammer moves as a very complicated system, but its motion can be treated as the entire mass of the hammer, which I can figure out. I could put it on a pan balance and measure its entire mass. Located at the center of mass position, which I can compute in principle. It's possible that I could do that, or I could do it sort of experimentally. The entire mass located at the center of mass position, moving under the influence of the net external force. Well, there are forces that hold the hammer together. There's no question about that. There are internal forces, each part of the hammer pulling on other parts of the hammer as it flips around and does its thing. However, the only external force, in principle, acting on the hammer is the force of gravity. Sure, there's some viscous drag and whatnot, but if we assume that the hammer moves rather slowly through the air, then the net external force is the force of gravity. So imagine the hammer not as something flipping around, but it's the entire mass of the hammer acting at the center of mass point, again, drawn here with a dot, with a vector drawn downward. That is the force of gravity. So therefore, as the hammer flies through the air, and I'm about to throw the hammer across the room, which, is pretty dramatic stuff. As the hammer flies across the room, it'll flip end over end like crazy, of course. But what I want you to try to do is to watch the dot that I've drawn on the hammer as the center of mass position, and you'll notice a very curious and satisfying thing. So here I go, throwing the hammer across the room. As you watch the hammer fly through the air, if you manage to keep your eye on the little black dot, you would discover that the black dot did not move around in swirling circular motion, but in fact moved along a parabolic arc exactly along the trajectory that I would expect for a marble shot from a spring cannon moving under the influence of gravity. So the center of mass position moves like a projectile, even if the rest of the hammer is doing something very complicated. And since many physical systems that I'll study have generally complicated motions, I'm going to find that this property of dynamic systems is a very huge advantage for me. The thing about my mallet here is that I've been trying to think of it as individual bits of mass. It's part of my system. But the reality of it is a continuous distribution of mass in space until I get down to thinking about it on the atomic level, which is certainly something that I'm not going to do in classical physics. So what I need is a way of computing the center of mass position for a uniform mass distribution in space, a mass that is distributed continuously through space, I should say. And so here, consider again my definition of the center of mass position along the x-axis, the center of mass 1 over the total mass times the sum from I equals 1 to n the number of particles in the system, mixi. This is a discrete sum. I write the sum this way because my system contains a countable number of objects, and I can label them all with numbers and count them up. But when I have a continuous object, like my hammer, I don't have a countable number of objects. And so what I do is I replace the sigma notation representing a discrete sum with the integral notation, which implies an infinitesimal sum. So here I'll write the position of the center of mass is equal to 1 over the mass, the integral of x dm. So imagine what I've done is I've divided my mallet up into infinitesimally small pieces. Since they are infinitesimally small, there's an infinite number of them, and it's uncountable. So the process of computing the center of mass position is performed as a feat of calculus, integrating from one to the other. So it's extraordinarily essential that we understand the technique of solving this integral for the practical purpose of finding the center of mass. But also, I want you to pay particular attention here because the techniques that I use in applying this integral equation for the center of mass position in this problem is a kind of mathematical technique that will repeat itself over and over and over again throughout our course, even in the second semester when we begin to study electricity and magnetism. So it's essential in two ways. It's doubly essential. Essential because of finding the center of mass position in continuous mass distributions, and also for the mathematical techniques involved. So what I'm going to do is, at first, is I'm going to solve a center of mass problem that I already know the answer to. That way I can be assured that my technique is working. I have here a meter stick, obviously 1 meter in length. And the mass of this meter stick, presumably, it's an extruded piece of plastic. Its mass is uniformly distributed. That is, the density of the meter stick is the same everywhere along its length. I'll show you a curious thing here. I'll place my fingers, one at the 0 centimeter mark and one at the 100 centimeter mark, and I'll begin to move my fingers closer and closer together, and you'll see that one finger starts and the other one stops, and one finger starts and the other one stops. A curious thing. The reason why they're stopping and starting that way is because the way the weight is distributed between my fingers affects the normal force between my fingers and the ruler, which affects the amount of friction force. So the finger that has the larger friction force is always going to be the one doing the pushing, and the other one's going to slide. But at any rate, no matter how I do this, no matter how carefully, slowly, rapidly, whatever, my fingers come together. You see here, they come together at the 50 centimeter mark. The reason why this happens is that the center of mass position of this ruler is at the 50 centimeter mark. That is, the average position of the mass of this ruler, quite naturally, rather obviously, I think, just a little bit of reason, is at the center of the ruler. I'm going to verify that by applying my center of mass definition, the integral form here, to a uniform rod. By uniform, I mean a rod whose mass is distributed uniformly along its length. And so I'll draw here, along the x-axis, a rod of length capital L. And I've arranged it horizontally so it's on the x-axis. I'll be doing this as a one-dimensional problem. And as I've said already, doing two-dimensional problems is not difficult. I simply extend into another axis. That is, I could calculate a y center of mass and a z center of mass. But here, laying along the x-axis, and I choose my coordinate system in which I want to solve the problems. Totally my choice, always is. So what I'm going to do is choose the right-hand side of the rod to be the position that I call 0, and to the right to be the positive direction. That means my rod just happens to lay entirely on the positive x-axis. So in order to apply this law, I have to divide my rod up into little differentials of mass. I have to make infinitesimal little parts of it. And the easiest way to do that is to, at an arbitrary position here along the length of the rod, slice it. An infinitesimally small slice that has a width dx. Now naturally, in that width dx, there's going to be a certain very, very small quantity of mass, dm. And that slice, dx, that I've drawn has a very specific position, x, in my chosen coordinate system. And so now I'm ready to set up the integral and solve. So just rewriting again for the sake of the argument, the center of mass position is equal to 1 over the total mass, and let's presume that I know the mass of the rod that I'm doing, the integral of x dm. Well, here's my problem. I don't know how to compute that integral because in order to do so, I need a relationship between x and dm. I'd be fine if the integral was x dx. That I know how to do because the differential matches the argument of the integral, so I proceed. But here it's x and dm, so I need to find a relationship, and this is part of the essential technique that's going to repeat itself throughout the course, so careful attention, please. I'm going to describe the rod in terms of its mass per unit length. That is, its linear mass density. We're all familiar with the concept of density. The density of the air in this room, for example, is the total mass of the air in the room divided by the volume of the room. Well, here my rod is one-dimensional. It goes along the x-axis. So I'm going to say the linear mass density, for which I use the symbol, the Greek letter lambda, is equal to the total mass of the rod, which in principle I know, divided by the total length of the rod. That is the linear mass density in kilograms per meter. Now, the linear mass density has the same property as all other densities. For example, I just referenced the density of the air in this room. If I compute the density of the air in the room by taking the total mass of the air and dividing by the total volume of the room, that density is the same density that I would find if I cup my hands like this and I make a little cavity inside my hands. The density of the air inside there, which I would compute by finding the mass of the air in my hands divided by the volume of the cavity I create in my hand, I would get the same density. Because the density is uniform throughout, and we assume that the density of the air is the same throughout. It need not be. Density can vary throughout, but in this particular case, I'm assuming that it's uniform in density, which means if the linear mass density lambda is defined as the mass per unit length, it is also the differential mass, dm, per differential length, which in this case is dx. Those two ratios have to be exactly equal to each other. They're both perfectly adequate ways of defining the linear mass density. Well, now here it is. I have my relationship between the differential of mass and the differential of position. Because a little bit of algebra moving it around gives me that the differential of mass is equal to lambda times the differential of position. So I can come back to my integral now and make that substitution of the constant linear mass density. It's the total mass divided by the total length. Those aren't variables, it's a constant quantity. So I bring it out of the integral. It is not a function of x. So I have lambda over m, the integral of x dx. As good a time as any to define the limits on the integration. I have to integrate over the entire rod. My rod starts at the origin of my coordinate system and it goes for a length L, so its final position would be L. So the limits on my integration are from 0 to L quite naturally. Well, the integral of x dx is a perfectly simple integral to solve. I know that it's equal to x squared over 2. So what I have is that my center of mass position is lambda over m multiplied by x squared over 2, where I evaluate the limits from 0 to L. Well, that naturally gives me lambda over m L squared over 2. And I could say, well, that's my final answer. But it's strange to have lambda, a contrived quantity, inside. You'll find when you're doing your problem solving that some problems will call for having densities in the answer. But in this case, I'm going to go for the answer to see if my predicted answer is the correct one. So what I'm going to do is replace lambda with what I know lambda to be equal to. Lambda is m divided by L. So the center of mass position along the x-axis is equal to 1 over m over L, L squared over 2. Well, I have immediately some cancellation. The masses cancel, certainly. And the L in the denominator cancels one of the L squared in the numerator. And so what I find is that my center of mass position is exactly what I expected that it would be. It is L over 2. Remember, that answer depends on my choice of coordinate system. Had I chosen 0 to be in a different location or chosen the positive direction to be a different direction or both, I would have gotten an answer that was algebraically different. So whenever I calculate a center of mass position, I have to be careful to understand that center of mass in the context of the coordinate system that I chose to solve the problem. This essential example of the application of the center of mass definition to a distribution of mass in space is the simplest that I can imagine. But now what I'm going to do, rather transparently I think, is I'm going to do the same problem again, side by side here on the board, except now I'm going to do it where the density is not uniform. That is, one end of my rod is less dense than the other end of the rod, and in fact, that the density itself is a function of x. So here, another essential calculation. I'll start again with the same rod. Difficult to draw it the same way, but here, a rod of length L, oriented horizontally along the x-axis here, and I'm going to choose my coordinate system the same way so that I can compare my two solutions and see what's different about them and what sort of challenges I get from it. So I'll set 0 to be the left-hand side of the rod and let it go along the x-axis to a position L. I have to proceed the same way because the integral that I'm going to solve is that the center of mass is equal to 1 over the mass, the integral of x dm, and I have the same problem I had before, the relationship between dm and x. And so I'll proceed exactly the same way. I'll slice the rod up into infinitesimal slices dx that contain within them a differential mass dm and have a very specific position in my coordinate system, x. And I'm going to use the density to make the relationship between dm and dx, but it won't be so simple. Because what I'm going to claim now, and I'm making this up, I could invent any kind of relationship for the density. This is just the one that I'm doing for this example. It's a simple one, but it will cause us a little trouble. Is imagine that lambda is equal to beta times x. And now beta is a constant that I invented. It's just some constant value that scales the density as it goes from 0 to L. But here's the thing. The density is now a function of x, which means at the origin, where x is equal to 0, the density is 0. And then as I go along from 0 to L, it becomes more and more dense. Because lambda is beta x, the density is increasing in a linear way. I could have made it the square, I could have made it the fourth power, I could have made it part of a sine function, I could have made it exponential, I could have made it anything I liked. But in this case, I made it linear. And so it has this dependence on x that it did not have before. It is still equal to the differential of mass, dm, divided by dx. That's still true. But I have a little bit of work to do before I can proceed with performing the integral. The work that I have to do is, I just made this up, and beta is standing in for some constant that I can actually figure out. The reason why I can figure out the constant, or how, the technique by which I figure out what the constant beta is to realize that lambda is always dm dx, no matter how complicated the relationship. So solving it around, the differential of mass is equal to lambda dx. I can integrate both sides of this equation. When I integrate the left-hand side, I'm integrating dm. Adding up dm means I get the total mass, which in principle I know. I still take this rod and put it on a pan balance of some sort and measure that mass. So I know what that mass is, and then it's the integral of lambda dx. Well, let me plug in what I know lambda is. It's beta x dx. Beta is a constant in this integration because it's not a function of x at all. It's the constant of it's the coefficient there. And so I can bring it out of the integral. It's beta times the integral from 0 to L of x dx. Again, an integral that I can easily solve. It's x squared over 2. And so evaluating the limits where m is equal to beta x squared over 2 evaluated from 0 to L is beta L squared over 2. That must be equal to m. And so to know beta, I simply solve for beta, and I find that beta is equal to 2m over L squared. And the reason why I've done this or gone through this trouble, you might say, well, Shadley, you could have told us that it was that when you defined the thing. The reason why is that this skill is sometimes required because in exams you might be asked to perform this particular task of finding out what those constants would be. So now I know not only that lambda is equal to beta x, but I know more specifically that lambda is equal to 2m over L squared x. So now that I know what lambda is, let me proceed the same way I was doing before. Let me remind you. I'm calculating the center of mass position along the x-axis, which is 1 over m, the integral of x dm. I'll replace dm with what I know dm to be equal to, lambda dx. But here's the key. In the previous version of this, the previous solution, I was able to draw lambda out of the integral because lambda is not explicitly a function of x, but now in this one it is. So I cannot draw lambda out. I have to replace lambda with beta x. And when I do, my integral becomes 1 over the mass, the integral of beta x squared, you see, because I have x times x, dx. Well, beta is a constant, and I know what it's equal to. I found it. It's 2m over L squared. So I might as well plug that in, 2m over L squared. So what I have out here in front of the integral is 2 over L squared, the integral, from 0 to L of x squared over 2. So the situation is more complicated, but as a result, I don't have a terribly difficult integral to solve. It's just getting to the integral was trickier. So it's the integral of x squared, which I know is x cubed on 3. So my center of mass position is equal to 2 over L squared, x cubed over 3, evaluated from 0 to L. Well, that's going to be 2 over L squared, L cubed over 3. Naturally, this L squared in the denominator cancels all but one of the L cubes in the numerator. So what I have for my final answer is that the center of mass position is equal to 2/3 L. That position is measured from the origin of my coordinate system, which I selected to be on the left-hand side. And so the center of mass is not at the center of this rod, but is 2/3 along. That means it's past halfway. And that makes a lot of sense to me, because my density is such that the rod becomes more dense as it goes along, which means more mass is further along, and that's going to shift the center of mass position from the center, where it would be for a uniform rod, and shift it out along further towards the end. And so 2/3 L is a perfectly acceptable answer for the question, where is the center of mass position for a non-uniform rod whose mass is distributed linearly